The universe is unimaginably vast, stretching far beyond what the human eye, or even the most advanced telescopes, can fully comprehend. Out there, countless planets and exoplanets orbit distant stars, each holding secrets we've only just begun to uncover. But how do we explore places so far away that even light takes decades, centuries, or millennia to reach us? For most of history, this challenge seemed insurmountable. Traditional methods of space exploration, while groundbreaking in their own right, were limited by the sheer scale of the cosmos and the complexity of its mysteries. Yet, in recent years, a revolutionary tool has emerged, reshaping our approach to understanding these alien worlds: artificial intelligence. By learning to sift through massive amounts of data, predict with unprecedented accuracy, and even simulate the unknown, AI is transforming how we map and study planets beyond our solar system. It's not just making exploration faster or more efficient, it's opening doors to discoveries we never thought possible. In this video, we'll dive into the groundbreaking role of AI in space exploration, uncover how it overcomes the challenges of mapping uncharted worlds, and explore what this means for humanity's timeless quest to find its place in the cosmos. Stay with us as we journey through a story of innovation, discovery, and the boundless curiosity that drives us to reach for the stars. Exploring distant worlds presents some of the most daunting challenges humanity has ever faced. Unlike the planets in our solar system, which we've studied through probes, rovers, and orbiters, exoplanets, those orbiting stars beyond our sun, are far out of reach. Even the nearest exoplanet, Proxima Centauri b, lies over 4 light-years away. To put that into perspective, if we sent a spacecraft traveling at the speed of the fastest probes we've ever built, it would take tens of thousands of years just to get there. Physical exploration, at least with our current technology, is simply not an option. That leaves us with one primary tool: our telescopes. But even here, the task is overwhelmingly complex. Consider the Kepler Space Telescope, one of the most successful missions in the search for exoplanets. Kepler stared at a single patch of the sky for nearly a decade, monitoring over 150,000 stars for tiny dips in brightness that might indicate a planet passing in front of its host star. From this mission alone, scientists identified thousands of exoplanets. But those small, intermittent changes in light only give us the barest hints about these worlds: their size, their distance from their star, and perhaps a clue about their atmosphere. And even then, the data from Kepler was vast and messy, requiring years of manual analysis, cross-checking, and validation by researchers. That's just one telescope observing one region of the sky. Multiply that complexity by all the new missions coming online, like the James Webb Space Telescope, which is now capturing unprecedented details of exoplanet atmospheres, and the scale of the problem becomes staggering. James Webb, for example, is designed to peer deep into the cosmos, detecting infrared light emitted billions of years ago. When it turns its gaze to exoplanets, it can search for the chemical signatures of life: water vapor, methane, or carbon dioxide. But analyzing the data it collects is like trying to piece together a 3-dimensional sculpture from 2-dimensional shadows. The raw information streams in at a rate that no human team could realistically process on its own. And this isn't just a problem with big telescopes. Ground-based observatories, like those of the European Southern Observatory, are also inundated with terabytes of data every night, much of it unstructured or buried in layers of cosmic noise. The sheer volume and complexity have pushed traditional methods of analysis to their breaking point. Furthermore, these methods have another critical limitation: they're rigid. They rely on predefined algorithms and human intuition, which, while clever, can only handle the patterns and anomalies we already know to look for. What about the phenomena we don't yet understand? What if there's an entirely new kind of planet or form of life or celestial mechanism that doesn't fit into the models we've built so far? Traditional tools struggle to adapt to the unknown, leaving gaps in our understanding of these far-off worlds. This is where the need for intelligent, adaptable solutions becomes clear. Solutions capable of handling massive datasets, learning from patterns within them, and even predicting what we might discover next. This growing demand has led to the rise of artificial intelligence in space exploration. By leveraging machine learning algorithms and neural networks, AI has the capacity to process data at levels far beyond human capabilities, all while evolving with each new discovery. It isn't just a tool for efficiency, it's a game changer, a way to break free from the constraints of traditional methods and unlock the secrets of the universe as never before. So, what exactly does AI look like in practice when applied to space exploration? Let's dive deeper. Artificial intelligence has revolutionized how we analyze the immense and intricate datasets gathered by telescopes and spacecraft, making the impossible not only possible but increasingly efficient and precise. In space exploration, particularly in the search for exoplanets, the data collected is mind-boggling. Telescopes like Kepler, TESS, and the James Webb Space Telescope generate terabytes of data that need to be combed through for patterns, anomalies, and faint signals that point to the existence of a distant planet. This is where AI truly shines, stepping in to handle the monumental task of processing and interpreting these massive datasets. One of the most innovative applications of AI in this field is through machine learning algorithms, the backbone of modern artificial intelligence. These algorithms are particularly adept at recognizing patterns and relationships in data, which is key when dealing with exoplanet detection methods like light curves, gravitational microlensing, and spectrometry. Let's break that down. When a planet passes in front of its host star, the star's brightness dims ever so slightly in what's known as a transit. This is a light curve, a visual representation of those subtle changes in brightness over time. To the naked eye, or even to traditional computational methods, these dips can look like random noise, especially when layered over the many other fluctuations caused by stellar activity or cosmic interference. But AI can sift through this data with incredible precision, identifying the telltale signs of a planetary transit by recognizing the unique and repeating patterns that indicate a planet's orbit. Gravitational microlensing, another detection technique, poses its own challenges. This method relies on the bending of light caused by a massive object like a star passing in front of another distant star. The resulting lens effect temporarily magnifies the background star's light, and if a planet is present around the intervening star, it creates a secondary signature in the amplification. These events are rare and fleeting, happening over days or weeks, and they produce complex data curves that are difficult to interpret. AI's ability to process this kind of multi-layered data has been transformative, enabling astronomers to identify planets that would otherwise remain hidden. Spectrometry, used to analyze the chemical composition of exoplanet atmospheres, presents yet another layer of complexity. By breaking down the light passing through an exoplanet's atmosphere into its component wavelengths, scientists can look for the chemical fingerprints of elements like water, oxygen, or methane. However, extracting those faint signals from the overwhelming noise of a star's light is akin to finding a single grain of sand on an entire beach. Machine learning algorithms excel at this task, identifying subtle spectral features far more effectively than ever before. Perhaps the most well-known success story of AI in exoplanet research comes from Google AI. In partnership with NASA, researchers trained a neural network to analyze Kepler data, a dataset so dense that even after years of analysis by scientists, much of it remained untouched. The AI was able to scour through this overlooked data and discovered 2 new exoplanets that had been missed by human analysts. What makes this achievement so remarkable is how it highlights AI's ability to work alongside human researchers, not replacing them, but enhancing their capabilities by handling the tedious and time-consuming tasks, freeing up humans to focus on interpretation and decision-making. The efficiency of AI doesn't just save time, it transforms the pace and scale of discovery. What used to take years to analyze can now be done in weeks or even days. And AI doesn't get tired, make mistakes from fatigue, or overlook faint signals buried in the noise. It's also constantly learning and improving, adapting to new datasets and refining its accuracy with every iteration. As a result, we're not only discovering new planets faster, but also gaining deeper insights into their characteristics, their sizes, compositions, and even the possibility of hosting life. This partnership between human ingenuity and AI-driven precision marks a profound shift in space research. By overcoming the limits of traditional methods, AI is enabling us to uncover worlds we would never have found otherwise, accelerating our journey to answer one of humanity's most fundamental questions: are we alone in the universe? And as we push further, AI's role will only grow, transforming how we look at the cosmos and reshaping our understanding of the universe itself. AI doesn't just help us find planets, it plays a crucial role in uncovering what these distant worlds might look like. When it comes to mapping planetary terrain, especially for exoplanets and moons we've never directly observed, AI pushes the boundaries of what's possible with the limited data we have. Imagine trying to reconstruct the surface of a planet light years away from just a handful of faint signals or atmospheric readings. It's like trying to piece together the image of an entire landscape from the reflection in a single raindrop. Yet, AI has made this monumental task not just feasible, but increasingly accurate and insightful. One of the most impressive ways AI achieves this is through 3D modeling. By using imaging data from telescopes and spacecraft, algorithms can create detailed 3-dimensional representations of planetary surfaces. For instance, AI processes data from radar instruments, spectral imaging, and even gravitational measurements to infer the topography of a planet. This technology has already been applied to worlds closer to home, like Mars and Venus, where AI-assisted mapping has reconstructed surface features obscured by clouds or rough terrain. For exoplanets, where direct imaging is far more limited, AI uses predictive modeling to generate educated simulations of what the surface might be like based on clues such as a planet's distance from its star, its size, and its atmospheric composition. Neural networks, AI systems inspired by the human brain, are particularly adept at handling this task. These networks are trained using known planetary data from our solar system, learning to recognize patterns that correspond to certain geological features like mountains, valleys, or oceans. They can then apply this knowledge to unfamiliar data, filling in gaps and creating plausible terrain maps for planets we've never visited. For example, if initial findings suggest a planet has a thick atmosphere and is located within the habitable zone of its star, neural networks can simulate the potential interactions between that atmosphere and the planet's surface over time, predicting everything from weather patterns to erosion rates. Generative AI takes this even further. Unlike traditional machine learning, which works strictly within the boundaries of existing data, generative AI can create entirely new models and simulations based on limited inputs. This means that even when we have sparse or incomplete data about a planet, generative AI can hypothesize what its surface might look like under different conditions. These hypothetical terrains aren't just artistic renderings, they're scientifically informed projections that help researchers test theories about a planet's geology and climate. For example, if we detect water vapor in a distant exoplanet's atmosphere, generative AI can simulate what an ocean-covered surface might look like, helping us visualize the planet's potential for supporting life. These AI-crafted maps aren't just academic exercises, they are instrumental in planning future space missions. Whether it's selecting a landing site for a robotic probe or identifying the most promising regions for resource extraction, accurate terrain models ensure every step of exploration is as efficient and safe as possible. For example, before the Perseverance rover landed on Mars, AI was used to analyze terrain data and generate detailed maps of the landing zone, helping engineers choose the safest spot for touchdown while maximizing scientific opportunities. In the future, similar techniques will guide missions to moons like Europa or Titan, where rugged surfaces and unpredictable conditions present significant challenges. Beyond their practical uses, these maps also play a vital role in determining a planet's habitability. By simulating surface conditions, AI helps researchers study factors like temperature ranges, tectonic activity, and the presence of potential biosignatures. These insights are essential for identifying planets that could support life as we know it or even life as we don't. By bridging the gap between raw data and meaningful interpretation, AI deepens our understanding of these alien worlds and brings us one step closer to answering the question of whether we are alone in the universe. This process of mapping planetary terrain is not entirely handed over to machines, though. AI works as a partner, not a replacement for human scientists. While algorithms can process data and generate models at incredible speed, human expertise is still vital for interpreting results and refining the maps. Scientists provide the context, creativity, and critical thinking that guide AI's work, ensuring that each discovery aligns with what we already know about planetary science while challenging the boundaries of that knowledge. Together, this collaboration between AI and researchers is creating a new era of exploration, one where distant worlds feel closer and more tangible than ever before. Determining whether a distant planet could sustain life is one of the most fascinating and complex challenges in space exploration. The conditions required for habitability, things like liquid water, stable temperatures, and key chemical ingredients vary widely depending on the planet. But finding this Goldilocks zone isn't just about distance from a star. To truly assess a planet's potential for life, we need to go deeper, analyzing its atmosphere, surface, climate, and chemical composition. Traditionally, this process was painstakingly slow and limited by what humans could interpret from the patterns in data. Now, thanks to artificial intelligence, we're making breakthroughs faster than ever before. AI excels at analyzing the factors that contribute to habitability. For example, one key area is atmospheric composition. By studying the light passing through a planet's atmosphere, scientists can break it down into its wavelengths, a process called spectroscopy. Each element or compound absorbs light in a unique way, creating a fingerprint that helps us identify what's present. AI plays a crucial role here, sorting through enormous datasets to find these faint, almost imperceptible signals that might indicate water vapor, oxygen, methane, or carbon dioxide. These aren't just random chemical markers, they're potential biosignatures, the telltale signs that biological processes could be at work. Take NASA's Exoplanet exploration program, for instance. Using advanced neural networks, NASA trains AI systems to recognize patterns in atmospheric data that could signal life-friendly conditions. A prominent example of this is the analysis of light curves and spectra captured by the Kepler and James Webb Space Telescopes. These AI models can detect subtle shifts in the data that humans might miss, such as the fluctuating presence of oxygen over time, something that could point to biological activity like photosynthesis. Another critical factor in assessing habitability is surface temperature. AI models can predict a planet's thermal environment based on its orbital path, star type, and atmospheric properties. But it doesn't stop there. AI also factors in planetary albedo, how much sunlight a planet reflects versus absorbs, and how greenhouse gases in the atmosphere might trap heat. All of this adds up to a clearer picture of whether the planet's climate can support liquid water, a fundamental ingredient for life. For example, researchers have used machine learning to study data about the Earth's climate and then apply those insights to exoplanets, predicting their long-term temperature stability. Beyond temperature and atmosphere, AI is helping scientists dig even deeper into chemical signatures that might hint at life. This includes searching for combinations of gases that typically don't coexist without biological processes. For instance, the simultaneous presence of methane and oxygen, which quickly react and cancel each other out unless continuously replenished by something like living organisms. In fact, AI recently assisted in identifying intriguing data from Venus that suggested the presence of phosphine, a chemical that could potentially be linked to microbial life. While the findings are still debated, the speed and precision of AI in detecting such anomalies show just how indispensable it has become. The implications of this habitability analysis go far beyond scientific curiosity. Understanding whether a planet can sustain life is central to humanity's long-term goals, including interstellar colonization. If Earth ever becomes inhospitable due to natural or human-caused events, finding a new home might not be just an ambitious dream but a survival necessity. AI enhances this search by not only identifying potentially habitable planets, but also modeling what they might look like centuries or millennia from now. By analyzing current data and feeding it into predictive models, AI can simulate how a planet's environment might evolve, whether its atmosphere will remain stable, how its star's activity might impact it, or whether geological processes could create a home for future settlers. All of this brings us closer to answering one of the most profound questions humanity has ever posed: are we alone in the universe? And if life can exist elsewhere, what does that mean for our place in the cosmos? As AI continues to refine our understanding of habitability, it not only enhances our search but expands our imagination, helping us prepare for possibilities we may not yet fully comprehend. Could these distant worlds someday become homes for humankind or reveal entirely new forms of life we've never even imagined? The role of AI in habitability detection is more than an exploration tool. It's a means of charting the future of life itself, both here on Earth and beyond. As we look toward the future of space exploration, one of the most exciting developments lies in the creation of autonomous AI systems, machines that don't just follow orders but can think, adapt, and make decisions on their own. Unlike traditional spacecraft or rovers that rely heavily on instructions sent from Earth, these AI-powered explorers are designed to operate independently, solving problems and making real-time choices far beyond our direct control. This autonomy is not just a convenience, it's a necessity when exploring distant worlds. Why is autonomy so important? For one, communication delays in space are a formidable challenge. For example, even at the speed of light, it takes about 20 minutes for a signal to travel from Earth to Mars and back. This delay makes real-time control impossible when operating a rover or spacecraft on a distant planet. Now imagine a mission to an exoplanet located several light-years away, where messages could take decades to arrive. In these situations, autonomous AI systems become humanity's eyes, ears, and hands, navigating treacherous terrain, analyzing data, and even repairing themselves, all without human intervention. We're already seeing the early stages of this technology in action. Take NASA Perseverance rover currently exploring Mars. It's equipped with an AI system that allows it to analyze the terrain and make navigation decisions on its own. This capability is critical because Mars is a rugged world filled with obstacles like sharp rocks, steep inclines, and loose soil that could trap the rover. Instead of waiting for instructions from mission control, Perseverance uses an algorithm called AutoNav to evaluate the safest path forward. It's not just about efficiency, it's about survival. Without this autonomy, missions could stall or fail entirely due to the inherent unpredictability of alien environments. Another promising project is AI for Mars, an initiative that trains AI systems to recognize and classify Martian terrain features. By feeding the AI thousands of images from previous Mars missions, researchers have taught it to identify hazards like sand dunes or rocky outcrops. This technology allows future rovers to adapt and learn from the environment in ways that humans simply can't simulate ahead of time. And it's not just Mars. Autonomous AI systems are being tested for missions to Europa, Titan, and other moons in our own solar system, where conditions are far more extreme and unpredictable. But what about missions to unknown exoplanets, worlds that we've never seen up close? This is where the potential of autonomous AI becomes truly groundbreaking. In the future, AI-powered spacecraft could serve as robotic pioneers, traveling to distant planets, gathering data, and even building infrastructure for human settlement. Imagine a spacecraft landing on an exoplanet, autonomously deploying drones to map the surface, taking atmospheric samples, and even starting to construct habitats, all while sending critical findings back to Earth. These systems wouldn't just be tools, they'd be explorers in their own right, carrying humanity's curiosity and ingenuity to the farthest reaches of the galaxy. Of course, creating machines capable of this level of independence comes with its own set of challenges. One major hurdle is ensuring that the AI can handle the unexpected. Space is an inherently unpredictable environment. From sudden dust storms on Mars to unknown forms of radiation near distant stars, AI systems need to be robust enough to adapt in real time. This requires rigorous testing and programming to account for countless potential scenarios. But even the most advanced systems can't plan for everything, which raises questions about how much autonomy we're willing to entrust them with. There are also ethical considerations. Should autonomous systems have the authority to make decisions that could alter the environment of another world? Could these robots accidentally contaminate pristine ecosystems with Earth-based microbes, or disrupt potential alien habitats in the quest for exploration? These questions don't have easy answers, but they highlight the need to balance technological ambition with responsibility. As we move forward, the integration of autonomous AI systems into space exploration represents a monumental leap in our ability to go farther and do more. These robots aren't just tools, they're partners, bridging the gap between what humanity can imagine and what it can physically achieve. And while they carry the weight of our hopes and ambitions, they also challenge us to think more deeply about the ethical and technical limits of exploration. What kind of legacy do we want to leave as we journey to the stars? It's a question that will shape the next frontier of human discovery, and AI will be at the very heart of it. Artificial intelligence is transforming how we approach one of the most challenging aspects of exoplanet research, understanding the environments of distant worlds we may never be able to physically visit. By simulating these alien environments with AI-driven models, scientists can predict what conditions might be like on planets light years away, helping us peel back the layers of mystery surrounding them. These simulations go far beyond what we can see from telescopes, allowing us to virtually recreate weather patterns, geological activity, and even the potential hazards that explorers might face. It's the closest thing we have to stepping foot on another world without ever leaving Earth. How do these simulations work? AI models are first trained on what we know about the planets in our own solar system and on Earth-like planets we've studied extensively. For example, researchers feed AI systems vast datasets containing information about atmospheric dynamics, surface composition, and climate processes. The AI learns to recognize patterns and relationships between these variables, enabling it to predict how similar systems might behave on other planets. When new data about an exoplanet becomes available, such as its mass, size, distance from its star, or atmospheric composition, the trained AI can use this information to simulate the planet's potential environment. Let's break this down with an example. Imagine an exoplanet orbiting within the habitable zone of its star, close enough for liquid water to exist but far enough to avoid extreme temperatures. By inputting its atmospheric data into an AI model, scientists can simulate weather systems over time, predicting phenomena like cloud formation, storms, or even seasonal changes. These simulations are critical for understanding whether the planet's climate could support life, or if it would be too volatile for human exploration. Similar techniques have been used to study Venus and Mars, allowing us to predict wind speeds, dust storm patterns, and even how their climates evolved over millions of years. But it's not just about weather. AI simulations also help us understand the geology of distant planets. For instance, by analyzing data on tectonic activity, volcanic processes, and surface temperatures, AI can model how a planet's crust might shift over time or how mountains and valleys might form. This becomes especially important when thinking about potential threats. On Earth, geological activity like earthquakes or eruptions can have a massive impact on the environment, and elsewhere, these forces might be even more extreme. An AI-driven model could predict areas prone to seismic activity on an exoplanet, helping guide future exploration missions to safer regions. These simulations also allow us to prepare for the unexpected. Space exploration is inherently risky. Our rovers and probes often face harsh, unpredictable conditions. By running different scenarios through AI models, scientists can explore what-ifs for a range of potential challenges. What happens if the weather suddenly shifts? How would a drone handle extreme winds? What if the surface is less stable than we thought? These questions can be explored and answered in the safety of a virtual environment before any spacecraft launches. It's like running millions of test missions without ever leaving a lab, improving the odds of success when we finally do go. One groundbreaking example of AI's role in simulating planetary environments is the Exoplanet climate model, a collaborative project designed to predict planetary climates based on various inputs. This software, powered by machine learning, has been trained on data from Earth and Mars to generate realistic climate models for exoplanets. By adjusting variables like atmospheric composition, radiation levels, and orbital eccentricity, the AI can simulate everything from tropical storms to global freezing periods. These insights are invaluable for determining whether a planet might be friendly or hostile to future human explorers. These virtual models are not just theoretical exercises. They directly influence how we plan future exploration strategies, particularly for interstellar missions. Take a hypothetical mission to settle on a habitable exoplanet. AI-driven simulations could help identify landing zones with the most stable environments, predict seasonal changes that might affect food production, or even calculate how human activity could alter the planet's delicate balance. By simulating and preparing for these factors in advance, we can avoid costly mistakes or unforeseen disasters, ensuring that future missions are as safe and efficient as possible. The impact of these simulations on interstellar mission planning is profound. As we look beyond our solar system and consider the possibility of sending crewed missions to distant planets, fully understanding their environments becomes essential. AI models give us the tools not just to imagine what these exoplanets might be like, but to make informed decisions about where to go, how to get there, and how to survive once we arrive. They prepare us for a future where interstellar travel could move from science fiction to reality, bridging the gap between what we know and what we dream is possible. By simulating the uncharted, AI is paving the way for humanity's boldest journeys yet. Whether it's uncovering the secrets of a stormy alien sky or predicting the stability of a far-off surface, these technologies are helping us write the next chapter in our exploration of the cosmos. And as we continue to refine these simulations, they'll guide us not only in discovering new worlds but in preparing for the moment when those worlds become destinations. What lies ahead isn't just the story of AI, it's the story of humanity's future among the stars. One of the most remarkable capabilities of artificial intelligence in space exploration is its power to predict cosmic events and changes with unparalleled accuracy. Predictive modeling, powered by advanced AI algorithms, allows scientists to forecast phenomena like meteor showers, planetary alignments, and even atmospheric shifts on distant exoplanets. These predictions are more than just fascinating insights, they are fundamental to mapping celestial objects, ensuring spacecraft safety, and developing long-term exploration strategies. By understanding what will happen in the future, AI not only helps us navigate the complexities of the cosmos, but also enables us to plan with a level of precision that was once unimaginable. Let's start with meteor showers and other orbital debris events. AI systems are being used to monitor and model the movement of asteroids, meteoroids, and space debris, creating forecasts that can prevent catastrophic collisions. For instance, NASA's Near-Earth Object Program relies on machine learning to analyze data from telescopes and detect objects on potentially hazardous trajectories. By predicting the paths of these objects, AI helps scientists determine whether they pose a threat to satellites, spacecraft, or even Earth itself. In the future, these predictive models could also guide spacecraft to avoid collisions with small but dangerous debris fields in otherwise unexplored regions of space. Planetary alignments offer another great example of AI's predictive capabilities. Alignments occur when two or more celestial bodies line up in a way that creates gravitational advantages, often referred to as gravity assists or slingshot maneuvers. These alignments are crucial for saving fuel and optimizing spacecraft trajectories. AI models excel at simulating these complex orbital dynamics, identifying windows of opportunity where a gravity assist can provide the optimal boost for missions traveling to distant planets or even other star systems. For instance, during the Voyager missions in the late 1970s, the alignment of Jupiter, Saturn, Uranus, and Neptune was used to explore all 4 planets with minimal fuel. While that alignment was calculated with traditional computational models, today's AI could analyze vastly more data and uncover alignments we might otherwise miss, opening up new efficiencies for interstellar travel. AI is also instrumental in predicting atmospheric changes on exoplanets or planets within our own solar system. By analyzing long-term atmospheric data and environmental clues, AI can model how a planet's climate might evolve. For example, the study of Martian dust storms, massive storms that can cover the entire planet and last for weeks, has benefited immensely from AI's ability to detect patterns in weather data. By forecasting these storms years or even decades in advance, future missions can avoid dangerous conditions or plan operations to take advantage of calmer periods. On exoplanets, predictive modeling might reveal periodic shifts in temperature, pressure, or even chemical composition, providing critical insights for assessing the planet's habitability. Another exciting application of predictive modeling lies in spacecraft navigation and resource identification. For long-term missions, AI can forecast the availability of resources like water ice on moons or asteroids, which are considered critical for creating fuel and sustaining life on extended explorations. By predicting the most resource-rich locations and the best time to access them, AI ensures that missions are both efficient and sustainable. Similarly, when planning planetary flybys, predictive models can refine spacecraft trajectories to ensure optimal data collection while minimizing fuel use. For example, AI-assisted trajectory planning was used in NASA's OSIRIS-REx mission, which successfully maneuvered to collect a sample from the asteroid Bennu, thanks in part to predictive algorithms that accounted for Bennu's irregular surface and movement. Looking at the bigger picture, the implications of AI-driven forecasting are profound. Predicting cosmic phenomena in advance isn't just about optimizing science, it's about mitigating risks and taking full advantage of fleeting opportunities. These capabilities will become even more critical as humanity looks beyond the solar system. For instance, being able to predict how interstellar dust clouds or radiation belts might impact a spacecraft could ensure the safety and longevity of deep space missions. Similarly, forecasting the potential habitability of uncharted exoplanets could help scientists prioritize exploration targets, accelerating humanity's search for another Earth. AI's role in predictive modeling represents a shift in how we think about space exploration. It's no longer just about reacting to what we discover. It's about anticipating what lies ahead, planning missions years or even centuries into the future. With AI at the helm, humanity's roadmap to the stars becomes clearer and more achievable, guiding us toward a future where interstellar travel might not just be a dream, but a carefully calculated reality. And as we continue to refine these predictive tools, they'll open doors to new opportunities and discoveries, enabling us to explore the cosmos with confidence and purpose. As we push the boundaries of space exploration with the help of artificial intelligence, it's impossible to ignore the ethical and philosophical questions that come with it. AI has undeniably become an invaluable tool in mapping unknown planets and seeking out signs of life, but its use raises complex dilemmas that go beyond data processing or predictive modeling. After all, when we send AI-powered systems into the cosmos, we're not just exploring, we're making decisions that could have profound implications for planets and ecosystems we don't yet fully understand. This makes the question of how we approach exploration and what guidelines we establish more important than ever. One of the most pressing ethical considerations involves prioritization. When AI identifies potential targets for exploration, such as planets located in their star's habitable zone or those rich in resources, how do we decide which worlds to study first? Should we prioritize planets with the highest likelihood of hosting life in the hopes of finding extraterrestrial organisms? Or should we focus on barren worlds that could one day support human colonization, minimizing the risk of disrupting an already existing ecosystem? These decisions could shape not just the trajectory of exploration, but the legacy we leave as a species venturing into the universe. Then there's the question of preservation. If AI-driven missions discover a planet capable of supporting life, whether microbial or more complex, what ethical responsibility do we have to protect that world from contamination? Earth-based microbes could inadvertently hitch a ride on spacecraft, potentially altering alien ecosystems before we even have a chance to study them properly. This is more than a hypothetical scenario. Even within our own solar system, planetary protection protocols are in place to limit contamination. For example, missions to Mars and Europa are subject to strict sterilization standards because introducing earthly organisms to these environments could compromise their natural state or obscure potential discoveries of native life. But as AI systems enable us to explore more deeply and autonomously, these safeguards may need to evolve, especially for unmonitored missions to exoplanets. The potential discovery of extraterrestrial life brings its own set of philosophical challenges. What would it mean for humanity to detect alien signals or biosignatures through AI? The moment would be groundbreaking but also deeply unsettling. Would we be prepared to recognize and respect the existence of another form of intelligence, particularly if it's one we can't immediately communicate with or understand? And if advanced AI makes these discoveries long before humans arrive, how would that affect the way we comprehend and engage with such life? These questions reveal a deeper tension. As we seek answers about the universe, we must confront uncomfortable truths about what it means to be human and our place in the cosmos. Moreover, there's the broader issue of how we balance curiosity with caution. Humanity has always been driven by a desire to explore and expand, but history has shown that unchecked curiosity can have unintended consequences. Colonization on Earth often led to the exploitation or destruction of native peoples and ecosystems, and the fear is that similar patterns could play out on an interstellar scale. The difference, of course, is that this time the decisions may not even be human-led. As we develop more autonomous AI systems, we must ask, can machines be programmed to value preservation over exploitation? And critically, who decides what those values are? This brings us to the concept of universal interstellar ethics, a framework that could guide how humanity interacts with unknown worlds. Such principles might outline what actions are acceptable when exploring or utilizing resources on alien planets, and emphasize the importance of leaving no irreversible damage. But agreeing on these ethics is no small task. Would these rules be created by a single nation, a coalition of spacefaring countries, or an international body like the United Nations? And how do we enforce these standards across missions led by different governments, private companies, or even future AI systems themselves? These are questions we can't afford to ignore as exploration ramps up in scale and ambition. Ultimately, AI will not only play a crucial role in the mechanics of space exploration, but also in shaping these ethical discussions. As it grows more advanced, AI could help identify potential risks to delicate ecosystems, or even simulate the long-term impacts of human activity on alien environments. In doing so, it might serve as both a tool for discovery and a safeguard against reckless expansion. But for that to happen, we, as the creators of these systems, must take responsibility for embedding ethical reasoning into their design. The future of space exploration isn't just about what we find, it's about how we choose to act once we find it. So as we develop AI and send it into the cosmos, we're not just exploring new worlds, we're also defining the kind of explorers we want to be. The decisions we make now, what we prioritize, how we approach unknown planets, and the protections we put in place will echo far into the future. Will we be stewards of the universe, driven by curiosity and respect, or will we risk repeating the mistakes of the past on a cosmic scale? The answers to these questions will shape not only the future of exploration, but also humanity's legacy among the stars. Artificial intelligence has undeniably transformed the way we explore the cosmos, bringing us closer to unraveling the mysteries of distant planets and exoplanets than ever before. From analyzing faint starlight to detect hidden worlds, to simulating alien environments with intricate detail, to predicting cosmic events years in advance, AI has become the cornerstone of modern space exploration. Its ability to process massive amounts of data, identify patterns invisible to the human eye, and adapt to the unknown has opened doors we couldn't have imagined just a few decades ago. What once seemed like science fiction, mapping planets light years away, predicting their climates, and even theorizing their habitability, has now become a reality, all thanks to the incredible power of AI. Humanity's ever-growing capacity to explore the stars represents not just technological progress, but also a deeper expression of who we are as a species. We've always been driven by curiosity, the urge to understand the universe and our place within it. AI has become more than just a tool in this pursuit. It's an extension of our collective ingenuity, helping us reach farther and solve problems that were once insurmountable. With AI by our side, we're not just finding new worlds, we're discovering new ways to think, to innovate, and to redefine the very boundaries of exploration. And yet, as much as AI unlocks, it also challenges us to reflect. With great power comes great responsibility. As we continue to venture into the unknown, we must ask ourselves, how do we balance the pursuit of scientific discovery with the ethical obligation to protect the environments we uncover? What kind of explorers do we want to be, and what legacy do we want to leave behind among the stars? These questions are not easy, but they're essential if we are to ensure that the next era of exploration is defined not only by what we achieve, but by the care and thoughtfulness with which we achieve it. The possibilities AI unlocks for future generations are exhilarating. Imagine a time when autonomous missions explore unknown galaxies, when interstellar travel becomes a reality, or when we finally answer the age-old question, are we alone in the universe? The tools we're developing today, fueled by the incredible capabilities of AI, are laying the foundation for these future milestones. And as much as this journey belongs to scientists, engineers, and AI itself, it also belongs to all of us. It's our curiosity as a global community, our shared desire to reach beyond the limits of our own world that drives this progress. So, as we look to the stars, we want to hear from you. What excites you most about the future of space exploration? How do you think AI can continue to shape our understanding of the cosmos? And how should we approach the balance between discovery and responsibility as we venture further into the universe? Let us know your thoughts in the comments below. This is a topic we believe sparks the imagination of everyone watching. If this video has inspired you, consider subscribing to our channel and joining us on this journey through the fascinating world of science, technology, and space exploration. Together, let's imagine what humanity's next great chapter in the cosmos might look like. The universe is vast and our curiosity is boundless. With AI lighting the way, the stars are closer than ever before. Let's explore them together.